Now let's define central potential. How do we define this the central potential? I mean, uh, suppose we have a three-dimensional physical system, and and these three-dimensional systems have they have central potential, and the potential energy, the potential energy that depends only on the distance from the origin. Suppose I choose an origin, say this is my origin. Now, the potential energy between this origin and another charged particle, uh, if it depends only on the distance from the origin, say r, this potential is called central potential. And and we can use basically spherical coordinates to actually parameterize over three-dimensional space. Now, a central potential it does not depend it does not depend on it does not depend on the angular variables like theta and phi that we have in spherical polar coordinates. And to take an example of the central potential is basically the Coulomb potential between electrically charged particles. If we have two electrically charged particles at a separation of r, then v of r, which is a scalar, is minus ze squared by 4 pi epsilon naught r. So assuming one to be plus charge and assuming another to be the negative charge. So this is an example of central potential, the Coulomb potential between electrically charged particles. So central potential, then what it means is that that for this, say, if I assume this is the position vector. Uh, if a person is at the origin of the central potential, what this person will visualize is he'll face the same situation everywhere surrounding him. So, central potential basically means that that you have a geometrical point where from everything surrounding that origin is symmetrical. There's complete symmetry with respect to that point of reference. And if we talk about, say, if we take the example of the spherical polar coordinates, suppose I choose a coordinate system like this, assuming this is x, assuming this is y, and assuming this is z, and choosing the position vector r. Then what I have is this angle is theta, and if I make a projection of this r on the xy plane, then the projection of r making an angle phi, which is called azimuthal angle uh, uh, with the x-axis, that's going to be the azimuthal angle. So the point here is that this r that we have, it can its value can vary from 0 to infinity. Then this theta can vary from 0 to pi, and this phi can vary from 0 to 2 pi. So I can write down the general potential. If I write down the general potential here, the general potential, say that's V of r, that's going to be the function of r, theta, and phi. And for the same situation, if I have to write down the central potential, the central potential V of r will be simply this r can be taken as scalar, so this V of r is V of r. So this is my central potential. Now, this the technique of central potential can be used in different situations and different problems. Like we can use it in isotropic 3D harmonic oscillator. We can use it in some spherical box, and we can use it in the simplest of what we call as hydrogen atom. And if I write down the Hamiltonian for hydrogen atoms, so if I write down it's p squared by 2m plus V of r. And for P, if I operate this momentum operator on some state vector, this is going to give me minus IH cross del of psi of r. Okay, psi of the ket of psi. So so what we can have here is that we can write down this this Hamiltonian operator as minus h cross square by 2m then del square plus v of r. Now this del square is it is the Laplacian operator, and there are many ways through which this this Laplacian operator can be written in spherical polar coordinates. So let me write down this Laplacian operator. This is 1 by r dou 2 by dou r2 of r plus 1 by r square times dou 2 by dou theta 2 plus 1 plus cot theta dou by dou theta, then plus 1 by sine square theta dou 2 by dou phi 2. All right. So this is my Laplacian operator. Okay. So I can use this Laplacian operator in this equation. Okay. So I can use it for the Hamiltonian. I can use it for Hamiltonian operator. So what will I get over here is I can write down this h as minus h cross square by 2m times 1 by r dou 2 by dou r square of r, then plus 1 by r square times dou 2 by dou theta 2 plus cot theta, then dou by dou theta, and plus 1 by sine square theta plus 1 by sine square theta dou 2 by dou phi 2. All right, and then plus v of r. All right. Now, if we rightly go back and we look for this, what we have, this is the angular part where this Hamiltonian is depending on the angles like theta and phi. And what we have here is that this this whole term, I can write down L square. And what's L square basically is, L square is minus h cross square times dou 2 by dou theta 2 plus cot theta dou by dou theta plus 1 by sine square theta dou 2 by dou phi 2. This is nothing but this whole thing is nothing but the square of angular momentum operator. So for this, this should be basically minus here. All right. So because this is multiplied, so this is negative. So I can use for this L square, right? So what will happen? This will become plus. So I can write h is minus h cross square by 2m 1 by r dou 2 by dou r2 of r, then plus. Okay. So what we have here is this whole thing is L square. So if I take only this much, this h cross square will be divided here. So what I'll have is L square by this h cross square will go down. This 2 will be multiplied to this. Okay, I'll keep it inside the bracket. So this will be h cross square r square, and then I'll close it. Then I'll write v of r. That should be the case. Now, this Hamiltonian has a dependence on r, and automatically it has a dependence on the angular momentum. This L is the orbital angular momentum operator. So we can see that this orbital angular momentum operator is composed of both theta and phi. Now, what's interesting here is that we can choose the problem the way like this. what we see here is that this L scar, it has a range of commutations linked with it. I mean, we have the we have the commutation between L scar and Lx, and what they do is they commute, and L scar and Ly, okay, L scar and Lz. So they give you 0. So if L scar commutes with Lx, what's important here is that Lx and Ly and Ly and Lz, they don't commute, but L scar and Lx commute, L scar and Ly commute, L scar and Lz commute, and what we have is we have L scar as we can write down this as Lx scar plus Ly scar plus Lz scar. So what we have the commutation between L scar and Lx. Now, if L scar is if it commutes with Lx, it should also commute with the Hamiltonian. So what it means is that the commutation between the Hamiltonian and this L scar gives 0. Now, what does it mean? It means that the angular momentum is a constant of motion, and if angular momentum is a constant of motion, it can simply be treated as a number in our original problem. So, what we have here from this equation point of view is we have the Hamiltonian, and this Hamiltonian has a dependence on the kinetic energy part. It has a dependence on the potential energy, and this Hamiltonian commutes with L scar. If it commutes with L scar, that means we can treat the two as the constant, and this motion can be considered as the constant motion. So what we have here is we have some compatible eigenvalue equations, what we call as compatible observables, compactable observables. And these compactable observables are Hamiltonian operator, and it's L scar, and it is Lz. So if I operate this Hamiltonian on, say, psi of r, I will have E psi of r. Okay, this will be my first eigenvalue equation, and then I can have an eigenvalue equation for L scar psi of r, and this we understand that this is L times L plus 1 h cross scar psi of r, and finally Lz operator on psi of r is going to give us ml h cross. All right, so so we can think of writing the solution for this wave function, and for this problem, and if I write down the solution, if I write down psi of r, the psi of r using the variable separable approach is going to give me r of r and y ml as a function of theta and phi. Now this is our radial part, and this is our spherical harmonics. Spherical harmonics. And this spherical harmonics, y, m, l, theta, and phi, they are same in any central potential. They are a number, they are a constant number for any kind of central potential. So they are same. They are same for any central potential. And r of r, the radial part, this r of r is different. It is different for every central potential. So it's going to be different for every central potential. So proceeding from here, if I write down the radial equation of a particle that's moving in a three-dimensional box, say for example, if I choose, say for example, I'll choose a single particle in one-dimensional box, I can write down its Hamiltonian as minus h cross scar by 2m t2 by dx2 plus v of x. All right. And if I write down the radial equation of particle moving in a three-dimensional box, that radial equation will be, say, minus h cross square by 2m d2 by dr2 plus L times L plus 1 h cross square by twice mr square plus v of r. All right, and choosing say then psi will give me E of psi. Now these two terms, which is basically, if we go back to the problem of spherical, if we go to the problem of hydrogen atom, what we have here is we have we have this term, this L times L plus 1 h cross square. This is the result of what